Thank you, everyone. I'm Hongpeng, and currently I'm a research scientist at Bytedance Seed. I'm mainly working on training infrastructures, and more specifically, I work on post-training RL infra. And I'm also one of the core contributors of the verl project. So today I'm presenting our RL training framework, verl. I will briefly talk about its key technical features and also some of our recent updates. So this talk will mainly cover the following 4 parts. So first, why is large-scale RL so important? And second, what are some of the system challenges for large-scale LLM RL? After knowing that, we will briefly introduce a little bit about verl. So why do people like to use verl to train their LLMs for reinforcement learning workloads? And finally, I would like to show some of our recent updates and show you what are on our roadmaps for now. So here comes the first question. So why is large-scale RL so important? So large-scale RL, especially for LLM, it is pretty important, mainly for, I would say, 2 reasons. Like the first reason is that large-scale RL makes LLMs have much stronger reasoning capabilities. So as you can see from the figure, some pre-reasoning, pre-RL time models like GPT-4o, it is not trained with RL. So when it is comparing to some RL-trained reasoning models like the first generation such model like O1, you can see there is a huge gap for reasoning tasks, for example, for mathematics, and probably also for coding and whatever hard problem that requires reasoning. So this is the first part why RL becomes pretty interesting. And except the reasoning capabilities that RL brings, another feature is RL helps us to build its agentic tool using capabilities. So for applications like deep research, browser using, or even when you're training a coding agent that can using LLM to write codes, all such kind of capabilities are generated when you train this model with RL as post-train. So because of the reasoning capabilities and the agentic abilities that brings by RL, it is becoming more and more popular, and people are showing more and more interest into how to train LLMs with RL. As you know, like RL is a pretty important recipe of the LLM training whole pipeline. Then as we are like infra engineers, we would like very natural to ask a question. So what are some of the system and infra challenges to train large-scale LLMs with RL? So from my perspective, the challenges of RL infra mainly comes to the following 2 parts. Like the first challenges arise from the diverse and complicated workflow that is inside such kind of RL training frameworks, RL training problems. As this figure shows, you can see we are showing 2 types of RL algorithms, which are gRPO and PPO. Both of them are pretty classic and are used by a lot of people. And for both these 2 algorithms, you can see there are a lot of algorithm modules there. For example, they all have the policy model that is generate trajectories, and also it will update the model itself. And also, except policy, we also have the reward model that gives us the feedback, and also it has a reference model which prevents the model to be trained too far from the base. And also for PPO, it also has a value model that predicts the long-term value. So given all these components, we can see the RL whole framework. It is actually composed of different modules, and each of them are running different programs and are taking different inputs and generate different outputs. So orchestrate such a workflow is pretty challenging. And also for such kind of algorithm modules, they are different, and their workload types are also pretty diverse. For example, for the policy model, it will do trajectory generation, which is largely decoding. And also, sometimes it will train, which is really compute-intensive forward and backward steps. And also, there are reference and reward models that is mainly do one-step inference. But also, there are some weight syncing from trainer to the general from time to time. So putting all these complicated things together, that we have really different modules and different diverse workloads, so it makes RL training pretty challenging. That is the first part of the challenge source. And the second part of the challenge source comes from the LLM itself. as we are training large language models, especially when it's pretty large, all the algorithm modules that I just described, they are not a single process. They naturally becomes a huge group of processes. So you have to orchestrate a group of processes for different modules with different parallelization strategies. And you want to make best use of the hardware resources to run them as efficiently as possible. So with this goal and all the workload and data flow challenges putting together, it makes RL training really hard and really difficult. So as we know, RL is pretty challenging. Then we would like to ask the question, so what did verl do to make the RL training really easy? So why people prefer to using verl to train their LLMs with RL? So the short answer is pretty short. It's just 2 words. It's flexible and efficient. So next, I would like to introduce some of the design details of verl. But before going too much into the verl system design, I think probably it would be better for us to revisit some of the classic distributed training and distributed machine learning design choices here. So as this figure shows, there are 2 types of design choices, which is a single controller and multi-controller design choices. So on the left-hand side of the slides, you can see it is a single controller. In single controller, there is a single controller there, controls a lot of the worker processes. And MPMD means there are multiple programs that are sitting on different worker processes, which means each single individual worker process, they may run different programs, take different input, and generate different outputs. And such kind of outputs could be an input of another process. It is a pretty flexible distributed machine learning paradigm because you can do whatever things, you can program whatever each component needs to do, and you just orchestrate them together. So it is a pretty flexible design. But on the other part, because there is always a single controller in the middle, therefore sometimes it has some scalability issues, and it is not super efficient comparing to the counterparts multi-controller. And some of the famous single controller machine learning frameworks, including the earlier version of TensorFlow, and also some classic reinforcement learning library like the RL. And on the right-hand side, we show the picture of multi-controller design. So in multi-controller, there is not such a single process in the middle. So basically, every single worker process controls itself. And the programming pattern follows the SPMD pattern, which means all the worker processes, they are programmed with exactly the same program, but they are getting different pieces of data, and they just start to run. And finally, in the end, they don't need to talk to any single controller for orchestrating. Probably there are some collective communication across these worker processes, but it's also not that expensive. Such kind of multi-controller design are classically, traditionally, most widely seen in scenarios like HPC or supercomputing scenarios. But now and more recently, they are gradually adopted by some modern machine learning frameworks like PyTorch and JAX. Multi-controller is a pretty efficient framework. However, it's not that easy to program, especially for reinforcement learning workloads where you may have different modules and they are doing really different things, having really different parallelization strategies. Then if you want to combine them together into a single process, it could be really difficult. So to solve this dilemma of single controllers' flexibility and multi-controllers' efficiency, later in verl, we introduce a new paradigm, which we call it hybrid controller. So the idea is pretty simple. You just combine the best of the both worlds. So in verl, we have a single controller, and we also have multi-controller. We have a single controller process in the middle where you can specify the algorithm's logic in the single controller. It controls all the input, output, and the RL data flow. And when you are specifying such kind of workflows in a single controller, later for efficiency, you can dispatch those real heavy lifting training and generation workloads into the multi-controller worker group processes under that. So in this way, we both have the flexibility of using single controller to specify the algorithm, and also we have a very efficient way to train the real heavy lifting training and generation with worker groups. So let's dive a little bit deep into the single controller first. So single controller just shows as this figure. From the developer's perspective, a single controller just as if you're writing a toy, really simple program, as if it is only lives on a single process. So on the code example here shows, it only have about 10 lines of code, but it's already include all the key components of PPO training recipes. Like you just call the actor worker group to generate sequences, and then you push those information into reward models, reference models, and critic models. And eventually, when you get some other information, you can use those things to update your actor and critic. So it is pretty efficient if you're an algorithm engineer and you can only just writing some simple code in the single controller, and then you can have a working recipe and working algorithms. So right now in verl, we already support a lot of algorithm recipes, including PPO and gRPO, which are relatively classic, and also some newer algorithms. And most of them are just coming into the world in like a few months from now. And I think it's part of because the flexibility of single controller. So it's really easy to integrate new algorithm into verl. So therefore, we are having a growing batch of recipes. So people would like to use it with single controller. So except from the single controller's flexibility, we also would like to mention something about the multi-controller's efficiency. So for verl, we really have strong support and integrate into a lot of the multi-controller-based training and generation backends. For example, for the training backends, we fully support frameworks like FSDP and Megatron. And for generation, we support engines like VLM and SGLang. And we also support all kinds of parallelization strategies and a lot of the highly efficient kernels. So putting all these together, the multi-controller parts can train the model and generate sequences really fast and efficient, and overall making the whole RL workflow runs pretty fast. So I think up to now, we have briefly talked about the key technical contributions of verl, of the single controller and multi-controller. And the rest of the presentation, I will mainly focus on some of the recent updates and show you what are planned on our roadmaps in the near future. So for the first updates I'd like to share, it is the Agentic RL training. So recently, there has been a growing interest in using RL to train agentic tasks. For example, the browser using and coding. However, such kind of agentic training is really different from the traditional RL training. For example, the RLHF. So as this figure shows on the top of the figure, it shows a workflow for traditional RLHF type of RL training, where in such kind of scenarios, the policy model usually only generates text tokens, and these tokens will be then forwarded to the reward model to get scored, and then to calculate some algorithm metrics, and then being sent back to the LLM model to update the model. It looks like pretty simple comparing to the counterparts, comparing to the agentic training scenarios. In agentic training scenarios, policy LLMs are not only generate text tokens, it also generates some richer contexts, some special tokens, and if you are training like coding agents, it will write code. So when you are writing code, it will not be directly put into the reward model to get score. However, it will first interact with evaluation environments, for example, the code sanding box. It will give you feedback like whether your unit tests are pass or fail, whether your compilation success or not. So when you're getting such kind of signals, it will then be streamed back into the policy LLMs to generate another round of code, probably fix some bugs and getting some better codes. And such kind of interaction may continue for multiple turns, and eventually it will finally finish, and the whole trajectory can be sent into the reward model to get scored and later being used to train this policy LLM. So as we can see in this new type of agentic RL scenario, the rollout is really different, and it generates real challenges for us to train such kind of agentic RL. So yeah, as we just described, the biggest difference between traditional RL training and agentic RL training lies in the route parts. So for traditional RL training, all the information are organized in a batched manner. So you get a batch of prompts and you send them into the LLM, and then later you get a batch of sequences and you use them to train. However, if we are still stick on such kind of synchronized version of LLM generation, it will cause a lot of trouble for the agentic tasks, because each individual sample may have really diverse timeline, and that could be really different. Like some of the sample may interact with environments for a long time, and some of them may interact just a few seconds, and some of samples may interact for multiple turns, and some of them may finish just 1 or 2 turns. So if we are still sending the information into LLM in a batched manner, then it will generate a lot of bubbles, just like the top of the figure shows. So later in verl, we introduce such async route scenario where each individual sample can have its own unique timeline. It is decoupled from other informations, decoupled from other samples, so that in this way we can remove a lot of the bubbles, just like the bottom figure shows. And this beautiful figure was borrowed from the Sky RL blog post. Yeah, so wrapping up what we have just mentioned in the previous 2 slides, finally we create a programming interface called agent loop interface. So in this agent loop interface, it acts as a bridge between the LLM generation engine and the environments. We are still making use of the powerful, efficient inference engine like VLLM and SGLang, and we are using their server mode generation API to work to generate information in this agent loop. But for the agent loop, the user also has the flexibility to specify whatever logics and whatever customizable logics you want to have to this interaction. For example, whatever environments you want to have, whatever number of runs you want to have, it all could be specified in this agent loop. And we're also making this agent loop to be an async API so that it can be called with high concurrencies so that hardware resources can also be greatly used. So except from the agent RL training, another update I would like to share is about verl is still pushing really hard to making our framework can really train with large MOE models. For example, the DeepSeek V3, which has 671 billion parameters. And right now, we already have a working recipe that can train such DeepSeek V3 model. And if you run it and giving some proper information and data, you have a chance to train DeepSeek V3 to something like DeepSeek R1. And currently, we are having a minimal example that is train this DeepSeek V3 model using just 96 H100 GPUs. And we are training this model using Megatron training backends, and also cross-node TP. And also, we verify that the curve looks pretty good. And we also have some planned optimization for it as well. So if you are interested about the details, you can check this GitHub issue tracker as well. Except from the things like we just mentioned, like the Agent RL and the large MOE model training, another really important efforts that we are also pushing is continuously refactoring verl to make it not only a RL training framework, but as a more standardized and customizable RL library. So, so in general, we have a plan to refactoring verl into the following 5 key components, like the route engine that is responsible for generating trajectories, the model engine that is responsible for define the model and also define how the model is trained. In the middle, there is a weight transfer engine that is transferring weight from the trainer to the general from time to time. And besides that, there are also 2 components, that is the agent loop that we just mentioned, and also a data transfer systems that is handling the RL data flow across a single controller and the worker groups. So a little bit more about this refactoring. Our ultimate goal is to making verl have a much cleaner API and making it a customizable RL library so that the user can import components of verl and building a customized RL workflow as they wish. And for the 5 components, I will briefly talk about probably 2 of them. So for the rollout engine, we would like to fully embrace the native server mode rollouts, which is pretty similar to what we have described in the Agent RL scenarios. Such kind of refactoring will make the connections and API more clear between the training engine and the generation engine. And it will also make it really easy for us to adopt any new features provided by the inference generation communities. The second part is the model engine. We would like to provide some much clean and better interfaces. And eventually, we want to making verl can be deployed as a service. And in this model engine, we will provide some standardized API, like initialize model, forward-backward steps, and optimizer steps, which looks pretty similar to the Tinker product released a few weeks ago. And after this refactoring, we will try to making verl also deployable, and you can customize this model engine to also do such kind of RL as a service things with verl. We also have some details about weight transfer engine, agent loop, and data transfer systems. But due to time limits, I will skip them here. But if you are interested about it, feel free to check this GitHub tracker. There are also some equally important things on our roadmaps. For example, the partial rollouts and fully async training pipelines, like lower bit quantization for rollout performance optimizations, better agent RL recipes, and support for multimodal data transfer. So feel free to check this GitHub tracker. You can see a huge bunch of recipe issues that we are currently working on. And feel free to join our GitHub and our Slack channel. Finally, I would like to thank you everyone for your attention to verl, for your contribution, and use verl and grow with us. Since we first released probably same time last year, we have grown a lot. And currently, we are having roughly around 15K stars, more than 2K forks and PRs, and roughly 400 contributors. And due to the contribution from the community, we currently having a lot of the recipes, a lot of capabilities, and also supports for all kinds of hardwares. And we're always looking forward to your participation. Thank you so much.
Thanks for that great talk, HP. We have time for questions. We've got one there, and I'll come bring you a mic. Just put your hand up.
Thanks for the talk. I had a quick question. In the beginning, I noticed even the diagrams you had were from the Pathways paper. I was wondering if you could say maybe what, like I know in Pathways, they make a point. They say, you know, you have single controller and you have multi-controller. And so they kind of introduce some things that let you, I think as I remember, use kind of single controller for multi-controller. I was wondering if you could say what is kind of qualitatively different or preferred in verl such that this hybrid architecture, like, presumably there's some kind of design difference here that makes verl better for certain things than doing Pathways. Could you say anything about the kind of difference or why you wouldn't just use the Pathways kind of primitives?
Yeah, I think that's a good question. I think for verl, we having the hybrid controller because I think for the algorithm parts, it's pretty easy to change because there are a lot of algorithms. And it is changing from time to time. So when you are having a single controller there, it will be really easy to adapt your algorithms and compose them as you want. But in order to have better efficiencies, we also need to have a multi-controller module that is doing the real heavy lifting. That's the idea why we decided to have this framework. So if you having, I think it's kind of like a two hierarchy. Like in the top level, it is a single controller where you have the flexibility to modify your algorithm things. But under that, we're still using the multi-controller that is having better efficiencies to orchestrate the real training and generation. I'm not sure if that answers your question. Thank you. Yeah, thanks.
Any other questions? Just raise your hand.
Thank you. Do you have any piece on the Ray direct transport features that just got released and whether or not that's integrated already into verl?
Oh, I see. Oh, I think that's a good point. Yeah, I think we having a group of engineers that is working directly with Anyscale about the Ray direct GPU transfer. And actually today we also have a part of our colleague, Wang, he is here. And he is part of the direct collaboration with Anyscale on this direct interaction, like how we can use the Ray direct GPU object store to transfer objects. I think probably after this talk, we can gather together and we can introduce Wang to you. Wang is also a key contributor of verl, and he also having some initial prototype of the single controller things. And I think we can have a better discussion offline.
Fantastic. Thank you.
Thank you.
Any other questions? Burning questions?
So in the RL training, so there's a lot of challenge for the long content length. Can you share some insight how the verl handle that?
Can you repeat the question?
So in the RL training, right? So there's a lot of challenge if we count length is very long, like 100K or 1 million tokens. Can you share more insight how the verl handle this long content length?
Oh, you mean when you are rolling out, there are the sequence length is very large. Yeah, I think currently we are having some things like probably as we mentioned, like in the final slides, we're having something like the partial rollouts. The partial rollouts is one solution that probably we can solve for this issue. So basically you can first, for the long tail problems, for example, you can having when the 50% of the samples are generated, you can just start to do training, and then you can pushing those not finished to a standalone genre to finish to continue training, continue generation, and there are also some fully async pipelines that is probably also used for the very long tail problems, because you are not bottlenecked by a synchronized steps that could also probably increase the performance.
Yeah, thank you. Another question. Yeah,
I'm just going to give someone else a chance.
May I ask you a question? So for this reinforced learning will be, could be used post-training after SFT. In how do you assess if it's ready to the reinforced post-training or not after the SFT? Do I need to do the DPO between or not? How do you assess it? And also for the DAP, and also recently they have a BAP. It's one is on policy learning, another is off policy learning. What's your opinion?
Oh, yeah. So I think the first question is about how do you decide whether the model is ready to do RL after your SFT? I think, to be honest, I'm not an expert about this. I think it's more about some of the algorithm recipes that how do you evaluate a SFT model is ready to be trained for with RL. I think probably you can follow some of the recipes, published paper about such kind of recipe. But for a frameworks level, I'm not a really best person to answer this question. And for the second question, I kind of forget about the second question, but probably we can continue this offline. Yeah.
Okay, last question.
Do you guys also plan on adding to your roadmap some address about the trainer and inference engine mismatch?
Can you repeat? Oh, sorry. Can you repeat the question?
Do you guys plan on also adding to your roadmap some solution to the trainer or inference engine mismatch?
Oh, you mean the deterministic of the genre and trainer? Yeah, I think we have a group of people doing such kind of things for the deterministic between trainer and general. Yeah.
Okay, I think that's time. Thank you so much, HP, and thank you for everybody's participation.
Thank you.